Okay, go ahead.
I was hoping you could give us some pointers for 8.5, the second part. At least in my case, like I figured out something that I think works, but proving it and showing the second part is going to be a hassle.
Okay, so which one is 8.5?
It's the one with number the permutation between the two vectors.
Okay.
And then the second part of it is showing that if there is an optimal solution that doesn't involve multiplying A and B, to prove or show that there is another optimal solution that does involve.
Okay. So as far as figuring out the greedy choice, I'm not sure exactly what hint to give you except to play around with some real vectors and see what works the best. All of the greedy algorithms we looked at, the proof that the greedy choice works is typically the same. In that you show that if you have an optimal solution that does not include the greedy choice, that implies that there's an optimal solution that does include the greedy choice, which means that it's safe to make the greedy choice. That making the greedy choice isn't going to get you in a situation where there is no optimal solution. So for examples of that, you look at the at 8.3, where the problem was the stopping at gas stations. Okay. And what was the idea there? How did we do the proof there? How did we prove that it was safe to make the greedy choice? Okay, so remember the problem is you've got a bunch of gas stations that are spaced at different intervals, and you've got to drive across the country, and you can only go a certain distance before you run out of gas. The question is, how few stops can you make? Okay, so I gave that problem in multiple choice form so that it would get you used to this way of thinking. So I don't mind talking about it right here. What is, if the greatest distance you can drive is some distance d, what is a greedy algorithm for figuring out the fewest number of gas stations you have to stop at? How do you choose the first gas station to go to?
Drive as far as you can.
Right, you drive the farthest one you can. You go the furthest one you can without running out of gas, which I guess would be this one here, and then just repeat. So on. So then, if that's your greedy choice, to show it's optimal, we need to show that if there is a itinerary, places to stop, that does not involve stopping at the gas station that's furthest from the start, but within range of the car, prove that you can turn it into one that does. So what's the proof of that? So let me get a better, suppose we had some gas stations like this, and this is our greedy choice, let's say, but someone hands us an optimal solution that involves stopping right here. So how do you prove that there is another optimal solution that involves stopping at the circled one, at the greedy choice? What's the argument you make? Yeah.
You can prove that since you can reach that one in d distance, you could also reach the next one in d distance that the optimal one does do.
Okay. So, yeah, the proof would be, let's look at the first two stops in the optimal solution. So the optimal solution will stop here, and then maybe it'll stop here. But it avoids the greedy choice. Well, I can take that solution. I know that I can go in one stop to the greedy choice. And that greedy choice is even closer to the next stop than this thing was. And so I can certainly make it to that spot, and then I can just pick up with the optimal solution, the other optimal solution. So I've replaced two stops here in the optimal solution with two stops up here. So if the first one was optimal, the second one's optimal as well. It's got the same number of stops, and it uses the greedy choice. So I've transformed the first solution into one that contains the greedy choice. Yeah?
Can your greedy choice solution be better than the optimal solution, or would that go against that the first?
Right. So optimal means best. So if we're assuming there's an optimal solution, we're not going to find a better one. We've just got to show that
You can
find one that's as good. Yeah. Yeah.
Sometimes in proofs like these, you would have an optimal solution, and then you would prove that it's not optimal. Doesn't making the greedy choice often prove that it's not an optimal, that the optimal solution that wasn't the greedy choice is next optimal?
Well, you sometimes prove something is not optimal by assuming it's optimal and going to a contradiction. But here, we're not reaching a contradiction. We're starting with what is assumed to be an optimal solution, and we're deriving from it a different solution that is the same length and therefore is also optimal. So we're not arriving at a contradiction. So with multiplying the vectors, it's the same thing. You've got a couple vectors you got to multiply. Dot product. And you've got, maybe the greedy choice is to multiply these two things right here, but the optimal solution does a different multiplication. So you want to show that you can, that by, there's some way to transform the solution that does not involve these optimal choices into one that does involve those optimal choices. Probably by, let's say that actually that the optimal solution that you have multiplies those two things together. So what I don't remember exactly how to do it, but probably you would look at sort of those four elements, leave the rest alone. Just got to somehow rearrange the optimal solution you have into one that involves a greedy choice. And it shouldn't be, it's not massively complicated or anything. It's just making the right argument. Any other questions? Yeah.
So can you contradict that the original solution is optimal and show that the greedy solution is better than or equal to? Is that an okay?
Yeah, so that's often what you would do, is you would say, I have some optimal solution O whose, we'll let that stand for its goodness or whatever. And you might show that here's one that involves a greedy choice, and you want to show that its greedy choice is better, the same as or equal to the other one. If the other one really was optimal, then G will also be equally optimal. They'll be equal. Yeah.
I'm going to show you where it's just with the caddis problem.
Mm-hmm.
Just having a hard time figuring out exactly how to make the greedy choice or resolve conflicts with making previous greedy choices. If that makes sense.
Well, I'm not sure what you mean by resolving conflicts.
Yeah, so if you pick too many people down the line, then you can't pick someone.
Right. So I know that other people have, but I have never been able to solve that problem by thinking of who to serve first. Okay? It is much easier, at least in my mind, to think about who can you safely put off till last. So let's just look at a few examples. Here's a greedy choice. Always pick the person with the most money and serve them first. Okay? Does that work? Okay, so give me a counterexample that shows that doesn't work. Yeah.
Someone with $2,000 who can wait 1 minute,
Okay.
and someone with $1,000 who can wait 0 minutes.
Okay. And that's fine. So if our greedy solution is to always pick the person with the most money who is still waiting in line, who hasn't had to leave yet, then when we face this problem, we would pick, there are two people in line. We'll pick the person with $2,000 and serve them, and then we'll look around and see who to serve next. All right? So why is that going to fail?
You can't serve the person with 1,000.
Right. So you're committed to this guy. You take his $2,000. This person goes home, and you only got $2,000 that day. On the other hand, if you pick the guy with $1,000 first, and then the one with $2,000 is still around after a minute, and you get that too. So you get $3,000. So what you got when you're coming up with your greedy choice strategies, try to shoot it down. Don't implement it and see if it passes the caddis tests. That's kind of slow. See if you can find a counterexample with 2 or 3 people that shoots it down, like we did here. That's usually all it takes. Just a couple, just a very small example will shoot it down. And rather than think about the problem backwards. Think about who can you safely choose to save for the very last, such that it won't. And when you figure it out, it's obvious that it's safe to choose that person. Okay? Yes.
So optimal substructure means that every single solution has to exhibit optimal substructure, right?
It means that an optimal solution contains within it the solutions to its subproblems.
Yeah, so essentially my question is, could you prove that a problem has optimal substructure by assuming that there's a solution that doesn't have optimal substructure and then like deriving a contradiction? So are all solutions to a problem with optimal substructure, do all of those solutions also exhibit optimal substructure
Yes.
or just a subset?
Yeah, all of them.
Okay.
Yeah, but we really haven't talked about proving that something has optimal substructure. We've sort of vaguely defined optimal substructure, but I haven't done a proof and don't expect you to do one like that. Any other questions? Okay. So we ended up last time. I'm gonna speed through a few of the slides we were looking at last time. To remind you what we were doing. We had looked at Kruskal's algorithm and we figured out that the complexity was simplified to this expression. So we got to sort the edges, so it's the cost of sorting the edges. Plus, we had to do E5 operations on this disjoint set data structure. And we had to do big union operations on the disjoint set data structure. And we were in the process of figuring out how to minimize the cost of sorting, the cost of finding, the cost of doing the union. And you remember the disjoint set data structure we're using worked like this. We've got, this is a disjoint set of A through H. So we start with a set of size 8. And the two fundamental operations are find and union. And what our set consists of is initially a set of trees that just have roots. And what happens over time as we do unions? What happens to our sets? Yep.
They all become one.
Every union operation will combine two trees into one. And ultimately, if you do enough unions, you end up with one tree. Now, is this a binary tree, a ternary tree? Or these, or I should say trees. The trees in this representation. How many children does a root have?
It's unspecified, it can have multiple.
Right, so it can have any number of children. So it's not strictly a binary or a ternary or anything. It just has any number of children. And let's see how that works. So to do a find operation, do a find on A, you start at the node for A. It's going to be in some tree. And from that node, you go to its parent, to its parent, to its parent, till you get to the root. Well, that's trivial in this case. You're already at the root. And then we report the letter in the root is what's returned by find. It identifies, to identify what tree. Find is figuring out what tree A is in. And find does that by returning the identity of the root. All right, so that's a find on A. A find on F, same deal. Now, how do you find the nodes? You know, it's one thing to say, okay, you go to A's node and then you work your way to the root. But we never talked about how you actually find the node before you start. You know, it's easy to see how you get to the root once you get to the node, but how do you get to the node? Looks like they're just floating out there in space.
Some sort of dictionary.
Yeah, you have to have some sort of dictionary, and we'll make this more concrete later, but you have to have some sort of dictionary that that pointed at these roots. But I've left that out of the picture. You'll see why shortly. So take the union of two things. You start at A, so you do a find on A, you do a find on B, and then you have one root point to the other root. And those numbers are ranks. They give the depths of the trees. And you always, when you're taking a union of two roots, you want to have the root that is in a shallower tree to point to the deeper tree. Why is that? Okay, I'll hold that question. But in this case, they were tied, so it didn't matter which way we went. But notice that when they're tied and one points to the other, the depth of one of them goes up, because now it's become a deeper tree. Okay, union of B and C. Okay, we find B's root, we find C's root, and we have C point to A, and notice that the depth of A did not go up. It's still a tree of depth 1. But what if the arrow had gone in the other direction, from A to C? C would have a depth of 2. So that's why we want to have the shallower trees point to the deeper trees so that no depths go up, because we want to keep these trees as shallow as possible. Really broad, shallow trees is our goal, because the complexity of these operations depends solely on how long it takes to get from a node to its root. So we keep those paths short, we're good. Okay, so find of C, we start at C, we go to the root, we report A as the result of that. Union of E and D, now that's like we've seen before. Union of F and G, that's familiar. Union of D and G, D's roots E, G's roots F. So we flip a coin, and one of them is the winner and gets a depth of 2. Okay, we do a find of G. We go to its root. We do a find of H, or do a union of H and D. I guess I left off the find of, okay, union of H and D. There's H, there's D, there we go. Union of C and H. Okay, first step is to find C's root. Next, we find E's root. Then we do the union. Okay. And then we argued that the worst case, in the worst case, if you do it this way, your tree cannot have a depth greater than log n. Okay, if you're lucky, you'll get a tree of depth 1. But you're not going to be worse than log n. I'm going to skip over this because we did the argument before. This sort of shows the worst case that you can do when you do a bunch of unions that creates a single tree and you end up with something of depth 3, which is log of the number of vertices. That's the worst thing that can happen. Okay, so this looks like kind of a crazy data structure with all this dynamic memory and pointers and this undrawn hash table that's pointing to mapping you from H to its node. Seems kind of complicated, and it is. But fortunately, we don't have to represent a data structure that way. We can do it this way. So we're going to represent it with a pair of arrays. So suddenly it gets a lot better. And so I'm going to use the vertex names as indexes. So that's in the middle there. And then I'm going to have 2 arrays, rank and parent. So rank is easy. Rank just gives you the rank of a node, the depth of the tree rooted at that node. Initially, every tree is at depth 0. And for the parent, I'm going to have, like, parent of C is always going to contain C's parent in the tree. And parent of F will contain F's parent. If something is its own parent, we'll denote that by storing the letter itself. So this tells us here that A's parent is A, that means A is a root. B's parent is B, that means B is a root. That's how we tell something is a root. So that's a pretty compact way to draw a tree. Why don't we do all trees this way? Why don't we do binary search trees this way? Yeah?
We can only go up.
Right. You say we can only go up. So if all you need to do is to go from the fringes up to the root, you don't need to go the other direction. This works great. This doesn't give you a way of starting at the top and working down. So binary search tree, you need to go down. Okay, so let's work through that same example and see how this representation gets modified. So to find A, what do we do?
Look at parents of A.
Yeah, you go to index A. I didn't highlight it, but you go to that index A. It takes you right to parent of A. You see that A is its own parent, so you know A is the answer. A is at the root of the tree. Same thing with find of F. Do union of A and B. We find A, we find B. Now what? Okay, one of them, I think it's B's parent is going to change to A. and A's rank is going to change to 1. Okay? So we're doing the same operations, we're just doing it on the arrays instead of on that dynamic data structure. Okay? Take the union of B and C. So you find B's root, you find C's root, and now C's parent will become A, and A's depth will stay the same. So right now, A, B, and C are all in one tree whose root is A, and the others are in singleton trees. Okay? We do a find on C. There it is. Now we're going to do a union of E and D. E, D, okay, that's just that case we saw again. This case, D points to E. We do a union of F and G. We find F. We find G. Voila. Union of D and G. We find the root. We find the root. And one's going to point to the other, whose depth will go up to 2. We do a find of G. Let's see, it goes to F. It goes to E. All right, let's do a union of H and D. H goes to itself, D, E. Now H points to E. So anyway, eventually we get to the end here. So how can you look at that and tell that that's all one tree? Everyone has the same root. Yeah.
Only one of them is rooted to itself.
Right. Only one of them has itself as its parent. Okay. Does this make sense? Yeah.
How do you know to set the rank to?
What's that?
How do you know what to set the rank to?
Okay. He asked, how do you know what to set the rank to? Okay. When you're doing a union, if you're taking the union of two things with different ranks, no rank changes. If you're taking the union of things with 2 ranks, the one that gets pointed to, the one that becomes stays the root, its rank goes up by 1. Yeah, the rank only changes. Let me see if I can find. I don't remember which one it is. Maybe D. Yeah, D and G. So if I take the union of D and G, I find D's root, I find G's root. Now, both of those trees have ranks of 1, as you can see. And so one is going to point to the other, and that other's rank will go up to 2. That's the only case in which a rank changes, is when you take the union of trees of identical ranks. And there it goes. So they all start out 0, and gradually they creep up. Any other questions? Okay, so that makes it a practical data structure. We don't have to be creating pointers and such. There's some code that captures what I was doing. For example, to create the find operation. We just say we're trying to find x. While x is not equal to its parent, x gets its parent. And when that loop ends, we return x. Here's the rank. You do a find. If they're already in the same tree, you do nothing. If Rx is greater than Ry, if the rank of Rx is greater than Ry, you have Ry point to Rx. Otherwise, do it the other way. In this case only, you increase the rank. So that'd be easy set to implement. And there's a final picture that shows 2 different looks at the same data structure. This is the data structure if we use real nodes with pointers, except I don't have the hash set that I would need, the hash map I would need. And there it is, done compactly in arrays. Okay, so we've got our operations. So it's easy to see back on this up there. The cost of initializing the data structure in the first place is O of n. We're going to have to create and initialize 2 arrays of length n. Find operation. How can I say that it's log n? What's the argument that find is log of n?
Log n is the maximum depth of the tree.
All right, we've already argued that the maximum depth of the tree the maximum depth the tree can reach within vertices is log n. And of course, initially find is constant. Not until the tree gets deeper that it starts to take longer to do a find. So that's an upper bound. It's not tight though. What about union? What's the argument that it is also log of n if there are n elements in the set?
Log n comes from finding the root.
Right, you have to do the two find operations. And then there are constant time after that, doing some comparisons and some changes. So that's the complexity of the operations, and if we plug it into Kruskal's algorithm, and we say, well, let sort be E log E, let's say merge sort. We're sorting those elements, sorting the edges, so it's E log E. This becomes E log V, that becomes D log V. And it turns out this term is bigger than either of those, or at least as big as those. And so far we have E log E as our complexity. And if we want to make the complexity any smaller, we got to find a way to do sorting faster. So let's see about that. So I'm going to teach you two sorting algorithms now. First one's called counting sort. So we're going to assume we're sorting an array of non-negative integers, like you see there. First step is just to count how many times each one occurs. So I just go through the array and I see, okay, 0 occurs twice, and 3 occurs never. There's no 3's up there. 6 occurs twice, and so on. How would you fill in this array? How complex is that operation? It's linear in, okay, the array is of length n. What's the length of this array here? It depends. Well, it depends on the difference between the largest element and the smallest element. I mean, here we just had to go from 0 to 9, because the only numbers up there are 0 to 9. What if the numbers up there went from 0 to 1 million? Right? And the complexity of this operation would be, you first have to create the million element array. That's going to take time proportional to m, to 1 million. Once you've got the array created, you can figure out these numbers in linear time, in O of n time. So the complexity of this depends on the length of that array and also the size of the numbers in that array. Because the bigger the numbers up there, the longer this array is. Well, we'll worry about that nicety later. Can you fill out that? Once you've created this array down here, can you fill it out in one pass?
In one pass of the top array.
One pass of the top array, right. You just go up there and say, I see a 5, you come down here and change this to a 1. Next time you see a 5, you come down and change it to a 2. So it's easy to fill out the counts. Okay. Now we're going to modify our array, and instead of having count of I be the number of times I occurs, I want it to be the number of times an element less than or equal to I occurs. All right? So what number would go here? How many elements are less than or equal to 0? Well, less than or equal to 0, there's 2. How many elements are less than or equal to 1? 3. So how would you get the number to put here?
It's that number plus the number.
Just add these two to get to 3. Right? How many numbers less than or equal to 2?
5.
5. So you would take this 2 and add to the 3 you just computed. So it's a really easy thing to do. Oh, I see. I didn't finish filling in the array up there. Okay. Oh. Okay, here it is on the next slide. So this is it filled in. Okay, I know what I did. Okay. You just sweep through the array, adding every element to the one to its left, right? So 2 and 1 is 3. 3 plus 2 is 5. 5 plus 0 is 5. 5 plus 1 is 6. And so on. So that transforms that array into that form. Okay, now we use the information in the count array to copy the information from up there to down here. We go right to left up in the data array. So we start with that one. We see a 2. We look down here and we see there are 5 elements less than or equal to 2. So where would the last 2 go in the sorted array? Assuming there are 5 elements less than or equal to 2. 1, 2, 3, 4, 5. These 5 elements are less than or equal to 2. So what's the index of the last 2 going to be? It's going to be 4. So what we do is we subtract 1. We look up the number of elements less than or equal to 2, which is 5. We subtract 1 from it. That gives us the index at which we store that 2 in the sorted array. So we're copying down. Okay? Now we see the 7. How do we decide where to put it in the new array? Same thing. Come down to 7, subtract 1, and then put the 7 at index 10. Again, we see a 4. There's 6 elements less than or equal to a 4. We subtract 1. We put the 4 at index 5. And we just keep doing that. 6, 10, that becomes 9. 6 goes to index 9. Okay? So that's counting sort. Now, right about now, someone always asks the same question, but no one's asked it yet. Yeah?
Could you speed it up at all by using a dictionary for the second array?
Speed it all up by using a dictionary for the second array. So you're talking about to avoid that array having to become
Right.
huge. That would make the operation where we make a pass through that array, adding everything to its left, more complicated. But anyway, we're gonna use this in a way in which the length of this array, the count array, doesn't matter. Yeah.
So I'm a little confused as to why we need to add up and get like all the number of elements less than or equal to I. Why couldn't you just figure out there's 2 zeros, so put 0, 0,
Okay.
and then
All right, that's the question. That's the one we always get, and I'm glad you asked it. So what he's saying is, this says there's 2 zeros. Why not just put 0, 0? Forget about that top array. It doesn't matter anymore. 2 zeros. In fact, don't do the adding either. So originally this said what? 1, 2, 2, I think. Before we, oh, 2, 2, 1, 2. Yeah, it was 2, 1, 2. There was 2 zeros, 1, 1, 2 2s. So why not just write 2 zeros, 1, 1, 2 2s, 4. When we first did the count, that gave us a recipe for filling this array out. Why bother with, adding things together to this and then going through this laborious process of sticking things into the slots instead of just saying, okay, I know how many zeros, I know how many ones, I know how many 2s, just fill it in. Yeah.
If you wanted to do it with double numbers, you could include those. If you were saying anything less than 1, you could have 0.7.
Okay, so, you're proposing sort of a different kind of sort maybe, where that's a reasonable suggestion, but there's a more concrete example. Yeah.
I think the main reason is if you have an array of a bunch of 1s and then a million, you'll have a bunch of 1s and then iterate through all of the numbers greater than 1 and less than a million until you get to a million.
Well, yeah, that's a problem in general counting sort. If you had a bunch of zeros and a bunch of millions, then your counting array would have a bunch of zeros in the middle.
Yeah, but iterating through and populating with 2 zeros and 3 1s like you've got here,
Yeah.
you would have to iterate through a bunch of values that have 0 entries. And so
Right.
iterating through that count list would be
Right, but yeah. But that's just, even if we do it this way, creating the count list is problematic in that case, when you've got big numbers. Still haven't given me the real selling point here. Yeah.
I would think that, although we're sorting integers, I would think that those integers might be an object paired with some other data value, and you need to preserve
Exactly.
data value.
Exactly. Here we're sorting integers. Imagine the ints are keys, and they carry with them values. So you can't just go throwing the keys in here and not even knowing what the values are. So as we're doing this illustration, just imagine that what you're copying down is not just the 2 and it goes here. It's the 2 plus the key, the value it goes with. You've got to copy the whole thing. And if we went through the step of just populating the keys, we would have lost the values. So it just makes it more general purpose to do it this way. Okay, so the complexity is O of n plus m, where n is a length of the original array, and m is the largest integer in the array. The n you can see where the n comes from. The m is the length of this array, and the cost here is just going to be filling in the array in the first place. It's going to take O of m time. So if m and n are the same, or close to the same, this is a linear time sorting algorithm. But if not, if m is much larger than n, then it can be a disaster. The other observation is that counting sort is stable. So who knows what it means for a sorting algorithm to be stable? Yeah.
So here, because we're starting from the end and going back, if you have two that are the same number, the one that was after the other in the original will stay after the other in the end. So
Okay, that's exactly right. So in a stable sort, if you have two elements in the array to start with that have equal keys, so let's say we've got a 2 here, and let's say its value is x, and you have a 2 here and its value of y. If the sorting algorithm is stable, in the final sort, in the case of ties, an element that was to the left originally will be to the left in the end as well. So these two things have the same key. So stable sorts maintain the relative order of things that had equal keys in the original array. So x and y have to appear in that order. If it was y and then x, it's still sorted, but the sort itself wasn't stable. So is insertion sort stable? Does insertion sort ever move an equal key past another equal key? No, because it only ever swaps things next to each other. It only swaps them if there's a less than. So a selection sort is stable. What about, insertion sort is stable. What about selection sort? No, in selection sort, you're taking an element here and an element here and swapping them. So any sorting algorithm that does swaps across a long range like that can easily move equal elements past each other. What makes counting sort stable? He said it, but someone else say it. What makes counting sort stable? How do we know that the two 2's up here won't change relative order while we do the sort? Yeah.
Because you go from right to left, and then you always insert it in the farthest position it can't be put in.
Exactly. We're moving from right to left, and we're always sticking the 2. The first 2 we find goes in the last spot a 2 can go in. The next 2 we see goes in the next one. So the relative positions are changed. So that fact's going to be important in a minute. Yeah?
Could you just reiterate the point about the key value here and how using basically that middle counting array and in coordination with the data array reserves the value?
Well, imagine that along with each of those keys up there, there was some kind of value. And then imagine we're filling in this array down here. We've got to copy down the key and the value for the sort to make any sense. So the strategy of going and saying, just looking at the count array and saying, there were 2 zeros, so I write a 0 here and a 0 here. I've lost the value. Value's still sitting up there. So what was proposed was just writing numbers in here without even looking at the data array again. Count how many zeros there are, or write that many zeros here, ignoring the data. We just can't do that.
Because it just doesn't look at the complexity of the object being stored.
Yeah, if you don't pull the things, if you are just saying there are 2 zeros and writing 2 new zeros here without regard to what the data was up there, you've lost the data.
So you could have a way of storing 2 different same key elements just from that middle array if you incorporated the value into the
So I guess you could say as you count, you can make a list of the data that went along with the key. Yeah, you might be able to make that work. But we're going to use this. Well, I'll just show you how we're going to use this so it doesn't matter. So the big problem with counting sort is the counting array can be massive. All right. So this is radix sort. So with radix sort, start with an array of non-negative integers again. Do counting sort, but by low order digit. So how long will the count array be? You're sorting these numbers, but we ignore their higher order digits. You're sorting them by their low order digit. Yeah. Yeah, you just need 10 elements in the counting array. Because there are only 10 different low order digits. And so you get this. You get 40 and then 21 and 81 up to 47 because you can see the low order digits are in order. Okay? Then do do counting sort again on the high order digits. Magically your array is sorted. So 2 passes of counting sort, 1 for each digit, 1 pass per digit, leaves you with a sorted array. How can sorting by low order digit and then sorting by high order digit be guaranteed to give you an overall sorted array? Couldn't the second sort mess things up? Yeah.
Counting sort is a stable sort, so it will never scramble the earlier digits.
Right. It's a stable sort, and so any ties the original order of the ties are going to be preserved. So, for example, look at the 2s up here, the 20s. Up here, 21 came first, then 22, then 26. That's not an accident. That's just the order of their low order digits. So when we did the second pass on the high order digits, the relative order of the 2s were maintained, meaning they're sorted by their low order digit. Right? People use this trick in Excel all the time. Excel uses stable sorts. You can sort by one key and then by another, and you've got it essentially sorted by both keys. So, what's the complexity of this counting sort?
2n, or 2n plus
2n. Right, it's just, you've got n keys, but your counting array is constant length. So it's just a couple of linear passes through the array. Now that's assuming you've got two digit numbers. But what if you have longer numbers? Yeah?
You just start with the low order and move up to the high.
You could say sort by the low order digit, then by the tens digit, then by the hundreds digit, and so on. Then it depends on the number of digits. Are digits the right thing to be talking about? Digits are great for illustrating this. Yeah? Can you think of a way to, what's the problem with sorting by digits? What's that?
Computers do bits.
Yeah, computers do bits. To get the digits out, we're going to have to do mods, right? To get the low order digit of a number, you got to take it mod 10. And that's an expensive operation. You don't want to do that. So perhaps we should be doing this by bits. What if we made one pass on the low order bit, another pass on the next order bit, and so on to the high order bit? That would work, but that's a lot of passes. Can you think of sort of a middle ground? Do it by bytes. Okay? If we did low order byte to high order byte, each byte is 8 bits. That's just a 256 entry counting table. So we can do Radix Sort that way. Make 4 passes, sorting by a different byte each time. There are 4 linear passes, and the counting array is fine. It's just 256 elements. So it takes linear time. So that is a linear time sorting algorithm. I thought we proved there wasn't such a thing. There's no comparison-based sorting algorithm. Okay? What disqualifies this as a comparison-based sorting algorithm?
It's not comparing 2 elements.
What are we doing? What are we assuming about the elements that we're sorting?
numbers. They're non-negative.
Well, we're assume they were non-negative. What are we doing with them?
Just moving them.
Well, we're doing something besides moving them. There's some property we're assuming about them.
We're calculating their indexes.
We're using them. Yeah, we're using them as indexes. Right? So that's not a comparison. We've got to be able. So you have a hard. Anything you sort this way, it's a special purpose sort. It won't always work. Suppose you took 32-bit numbers, but they were in 2's complement, and sorted them using Radix Sort. Okay? Just using this algorithm I told you here, without any changes. How would the numbers come out if you sorted them using Radix Sort?
Negative numbers would be the very end.
The negative numbers would come at the very end, because the algorithm is going to interpret the 32 bits just as unsigned numbers. So the negative numbers all have a 1 in the high order bit, so they'll come last. So you'd end up with the positive numbers. You start with the 0, followed by positive numbers, followed by negative numbers. The positive numbers would be in ascending order. What would happen to the negative numbers? They'd be in descending order. Because the viewed as an unsigned number, the largest two's complement number is -1. It's all ones. So could you use Radix Sort to sort signed integers?
You just reverse the end of it.
Yeah. You could sort them using Radix Sort, and then you'd have to make another pass to deal with the negative numbers and put them at the beginning and turn them around. You can sort floating point numbers. IEEE floating point standard is designed so that you can sort them using Radix Sort with an additional pass to deal with the negative numbers. So why don't we see Radix Sort in the Java library? It's linear.
It can't really be generic.
Yeah, he said it can't really be generic. Basically, anytime you use Radix Sort, it's a special case. Okay? It's easy to sort unsigned integers using Radix Sort. If you've signed, then you've got to say, oh, after I do the sort, I've got to make this change. Or if you're sorting floating point numbers, after I do the sort, I got to do this change. So every case is different. So it's not general purpose. With comparison-based sorting algorithms, you just define how to compare, and then it's generic. All right. Now, what if we were sorting integers containing k bytes? So big integers containing k bytes. There are n of them that we're sorting. Each one contains k bytes. What would be the complexity of Radix Sort then? Well, okay, what's the call? How many passes will we be making? K passes. And what's the complexity of each pass? N. So it's just k times n. But I claim that's linear. How can I claim that's linear time? Yeah?
K can be represented as a constant.
No, k is not a constant. We don't know. Our numbers have k bytes, and k can be large. That's not it. Yeah?
It's linear with respect to data structure.
Yeah. How many bytes are we sorting total? You have n integers, each with k bytes. How much stuff do we have? How many bytes do we have to sort? Kn bytes. So this is linearly proportional to the size of the data structure. I give you kn bit integers, kn byte integers to sort, and it takes time proportional to kn. So that's the definition of a linear algorithm. So yeah, Radix Sort's great. It'll blow away quicksort on, arrays of integers. Yeah.
So we could perform Radix Sort on any kind of data type as long as we can convert each type into an integer of some sort that is comparable with its others.
They don't have to be comparable. You have to be able to sort it using counting sort. You have to figure out a way to sort your data using a counting sort, which means you're going to have to turn your data into array indexes such that if this element is less than this element, the array index is less than the array index. Yeah. So you have to get that mapping from data elements to non-negative integers. You can do that. You can do Radix Sort. Yeah.
Could that be accomplished with like a cryptographic hash function, or would that just be too costly to do that?
That sounds pretty costly.
Okay.
And I'm not sure how you would guarantee that if this is less than that, then the index you would get would have the same relationship. Okay, so that's nice. Now if we look at the complexity of this, we've got O of E for our sort now. Use Radix Sort. We just assume that the things in the nodes are non-negative integers. And so now it simplifies to O of E log D. We can do even better. what we're going to do now is, or maybe not now, but we can go back to the union find data structure and make it faster and reduce this down even more. Let's take a break. Okay, so I've promised you that we're going to see a way to improve the union find data structure, but I'm not going to do that right away. I'm going to do it next week. Instead, I want to introduce a new topic, and that's dynamic programming. So let's do dynamic programming. All right, so here's a problem to introduce the idea. So imagine you got a steel rod n meters long, and you've got a table, and it says if you have a 1 meter steel rod, you can sell it for this many dollars. If you have a 2 meter rod, you can sell it for that many dollars. And just imagine this is this weird economy where maybe a 2 meter rod is worth $10, but a 3 meter rod is worth $11. So it's not a simple table. And you want to figure out how to chop your rod up into pieces so you can sell it for the most. Okay? So here's an example. 6 meter rod, and 0 meter rod you can sell for $0. 1 meter rod for $1, 2 meter for $1, and so on. So if that's your table, what are your strategy going to be? How can you maximize your profit? Yeah?
Go for 3-meter rods.
Or if we cut it in half, we can sell the 2 halves for 8, right? Anyone see a way to do anything any better? I don't believe so. We could sell the whole thing for 7. We could cut it into 5 meters and 1 meter and sell it for 7. Yeah. But 8's the best we can do. That's the sweet spot. Okay. There's the answer to this. Is there a greedy algorithm? Probably not. No one's ever found one, and most people believe there isn't such a thing. So, let's fall back on something that's guaranteed to work. Try all the possibilities and see which one works best. So here's my code. I'm asked to find the rod profit, the maximum profit, given a table of values. And I'm going to assume that the length of the rod is essentially the length of the table. And, or one less than length of the table. And this is my helper function. So it says, okay, I've got a rod of length n, this is my table of values, what's the best I can do? And all I do is I set max profit to 0, and then I say, okay, let's look at every possible cut I can make. I can let I be n, which means I'm going to sell the whole rod, or I can let I be n minus 1, which means I'm going to cut off n minus 1 meters, sell that, and see what I can do with the 1 meter that's left. Or I'm going to cut off n minus 2 meters, and continue like that. Well, yeah. So I'm looking at all the places I can cut the rod. And I'm going to sell one of the pieces, and I'm going to consider cutting up the second piece and see the best I can do. So values of I is going to be what? So I've cut the rod into 2 pieces. What's values of I?
The price at that point.
That's what I can get for the piece that I cut off. And what's rod profit of values and n minus I? That's the maximum profit I can get if I repeat the process on the leftover piece of rod. Maybe I want to sell it whole, maybe I want to cut it into pieces. Okay? So the point is, I choose where to cut the rod. So I cut the rod into a left piece and a right piece. I sell the left piece, and I repeat the process on the right piece of figuring out where to cut it until no more cuts. So I'm choosing a series of cuts. If we had a greedy algorithm, it could just tell us, make the cut here, make the cut there, make the cut there. I'm considering all the possibilities. So for each place I might cut it, I figure out the profit, and I see if it's better than my max profit so far. When I'm all done, I've found the overall solution. So I'm iterating through cuts, and I'm doing recursion to figure out how to solve the subproblem. So each cut produces one subproblem. Make a cut, sell part of it, I've got a new subproblem to solve with what's left. So what do you think of the solution? Long in what sense? Fits in one slide. Yeah?
Once you start iterating through it, the complexity would be factorial, or at least really expensive.
Yeah, it's an exponential algorithm. If you do like n equals 30, it won't finish anytime soon. I mean, it's noticeably. No. You don't have to get n very big before you'll take effectively forever. Okay, so what we'll see is that with dynamic programming, that the first step is to come up with a recursive solution that basically tries all possibilities systematically. So dynamic programming is for solving optimization problems like this. It's for solving optimization problems that exhibit the optimal subsequence problem, property, which turns out this does, but for which you can't find a greedy choice. So you write a recursive solution that tries all the possibilities, but there's a trick. Before we get to the trick, though, I have to warn you that if recursion is something that you have been hoping for the last few years you would finally hear the end of, you're out of luck, because It's inherently recursive. Dynamic programming, you just can't talk about it without recursion. So this might be the point where you finally get recursion if you don't get it now. All right, so there's our, let's look at it. So if we're dealing with a rod of length n, think about the recursive calls we're making. We're making a recursive call, you know, we cut off 1 meter and then try to figure out what to do with what's left. That's one recursive call. We cut off 2 meters and see what we can do with what's left. We cut off 3 meters, 4 meters. We cut off, we just sell the whole rod and then we have 0 left over. Okay? Plus we've got linear amount of overhead in the loop. Okay? So that's just, you know, and then, so T of n makes all these recursive calls. It's got a loop that makes n recursive calls. This guy's going to make n minus 1 recursive calls. This one's going to make n minus 2 recursive calls. So a lot of recursive calls are happening, especially if n is large. All right? So I'm going to, this thing here is bad enough, but it's, you know, it's even smaller than that. So I'm just saying this up here is greater than or equal to t of n minus 2 plus t of n minus 2 plus theta of n. I threw away some of the terms. I'm just saying, suppose you just make 2 recursions. Okay, so that's that. Then I threw away the theta of n. I made it 1. And it turns out, if you look at that, it's just that geometric series, which is greater than or equal to 2 to the n over 2. So the complexity is at least square root of 2 to the nth power. Okay, so it is exponential. So not a practical solution. Okay, so let's look more carefully at what's happening. RP, what's RP stand for? Rod profit. Rod profit of 30 makes, you know, it's in a loop considering all the places it can make a cut. It makes those 30 recursive calls. It calls RP of 29, it calls RP of 28, it calls RP of 27, and so on down the line. That's what RP of 30 makes. What does RP of 29 do? Yeah, almost the same thing. It calls RP of 28 on down the line. RP of 28 calls RP of 27, RP of 26. You see what's happening here? Right, we are making the same recursive calls over and over again. How many different recursive calls are there if you start with n? They're just, right, they're just 30 distinct ones. There's RP of 30, there's RP of 29 down to RP of 0. Those are there are only those parameters that you can pass to RP. So that means we are calling the method over and over and over again with the same parameter and computing exactly the same result each time. So if you're in that situation where you've got an exponential number of recursive calls flying around, but there are only a small number of distinct recursive calls, then you apply dynamic programming. So RP of 29 is only called once. How many times is RP of 28 called? You can see it twice up there. How about RP of 27? Well, let's see. It's called up there on the first line, RP of 27. Yeah, and then RP of 29 is going to call it. RP of 28 is going to call it, and this RP of 28 is going to call it. All right? So this call to RP 28 is going to call RP of 27. So is that one on the top line. And we call it directly in 2 other places. So it's 4 times. And you see where we're headed. It doubles each time. So that's exponential. We end up calling RP of 0 an incredible number of times. Yeah?
Isn't RP 28 called 3 times and 29 called twice then?
Well, 29...
You can see 28 3 times on there and 29 twice on there. So.
Well, no, just look on the right side.
Okay.
You see 28 twice on the right side of the calls. But the exact count's not important. It's just that it happens a lot. So can you think of a way to avoid this mess? Yeah?
You just store the value once you calculate it once.
Right. Change the method so that it remembers, change the problem so that when you calculate RP of 28 the first time, it remembers the answer. And the next time RP of 28 is called, it just reports the answer. it doesn't go do this massive recursion to compute it again. That's dynamic programming. And here's the idea. So the yellow is the changes. I've added a cache. So it's a dictionary, a hash map, and it maps from things that are parameters to rod profit, namely n. It maps from different values of n to the maximum profit you can get with something of that value. So let's see what happens. When we enter the method and we're asked to find the maximum profit with n, first thing we do is we go see if we already have computed this subproblem n. If we have, we just return its saved value. Then we do what we did before, but before we return the answer, we cache it. So we store the fact that, okay, the answer for n is this max profit is computed, and we return it. So the first time this thing is called, it does its recursion. The next time it's called, it returns in constant time. And I want to emphasize, this is the easy part. The dynamic programming part is easy. If someone hands you a recursive solution to a problem, and it's massively inefficient, and you realize it's inefficient because it's solving the same subproblems over and over again, it's easy to I call this memoizing. It's easy to memorize it. You know, it's a simple transformation to the method. You just add some code at the beginning to look up the answer, and some code at the end to store it. And that can make a huge difference. So let's think about it. So dynamic rod profit makes those recursive calls. So those 30 recursive calls, let's say. Okay? So those calls are going to take time proportional to n minus 1, just the calls themselves. Okay? What happens when DRP of n minus 1 runs? Well, let's say DRP of n calls DRP of 1 first. So it calls it, its answer is cache. Okay? Now what's DRP of 2 going to do? It's going to call DRP of 1, but that's already been answered in cache. Okay? So finally we get around to calling DRP of n minus 1. It calls DRP of 1. The answer is cache. The answer is cache. The answer is cache. So there's no recursion involved at all once things have been called once. So that just means that at the top level, we make those 30 calls. The next level, we make 29 calls. The next time, 28 calls. So what we end up with is an n-squared algorithm. So we've turned square root of 2 to the nth, actually something worse than that, to n squared, just by caching. It makes a dramatic difference. So if memoizing the code is the easy part, what's the hard part? Yeah, that's what you ought to find the hard part. Sometimes students find even the memoizing hard for some reason, but the coming up with the recursive algorithm in the first place is typically the challenging part. Once you've got that, you can test it out for small numbers and see that it works, and then memorize it, and it can work for large ones. So with dynamic programming, you got to have an optimization problem. It's got to have the optimal substructure copy, because you got to be able to solve the subproblems and save them and use them. If you can use a greedy approach, please do. But if you can't find a greedy choice, or if there is no way to make a greedy choice, you can use this. And if the exhaustive recursive solution is grossly inefficient, because it solves the same problems over and over again, then you can use dynamic programming. Sometimes recursive solutions are exponential because they're an exponential number of subproblems. That won't work. you've got to have a recursive solution that's taking exponential running time to solve only a polynomial number of distinct problems. If you can set that up, then you can memorize it and make it faster. So there's the fun part and the easy part. How can you go wrong? Now it takes practice. So here's another problem. This is more practice, and there's the next caddis problem is a dynamic programming problem. But I want to point something out. Before you start working on the caddis problem, be sure that you at least look at the description of the problem in Canvas, because I think it's like problem 9.5 is the caddis problem, but problem 9.3 is going to be leading you through the process of finding a recursive solution. So you should do the 9.3 quiz before you do the 9.5 quiz, because it helps you with the coding. So do it in the right order. All right, so let's just introduce this problem, talk through, and we'll spend all of next week, probably more, talking about dynamic programming. Given a sequence of integers, like you see there, find the length of the longest subsequence in which successive elements are strictly increasing. So by subsequence, I don't mean contiguous. I just mean throw away some numbers, so what you've got left is in increasing order. And I want what's the most numbers you can have left in that process. So clearly, if we threw away everything except the 5, we would have an increasing subsequence. If we threw everything except the 2 and the 7 away, we would have an increasing subsequence of length 2. Is there a sequence of length 3, a subsequence of length 3? Okay, like 2, 2, 3, 6. Is there one of length 4?
2, 3, 6, 7.
Yeah, 2, 3, 6, 7, or 2, 3, 6, 9. And there's not one of length 5. So the answer would be that there's one of length 4. So we'll focus on that problem. Inevitably, students ask, okay, you've told me how to figure out the subsequence of length 4, but what is the subsequence, right? And that rod profit problem, I told you a way to figure out the maximum profit, but that doesn't do you any good unless you know where to make the cuts. So that's a related issue we'll talk later. How do you actually recover? You can find out the value of the optimal solution, but how do you find out the choices that were made? But that's not hard, it's just a separate issue. So there's a solution, an optimal solution there. And there's not a greedy solution anyone knows about. But you can come up with a recursive solution, and this is how I'm going to do it. I'm going to define longest of I to be the length of the longest increasing subsequence that starts at index I. So what would be longest of this index here, whatever that index is? What's the length of the longest increasing subsequence that starts at that index? 1. What's the length of what is it for here? What's longest of this index? 3. 3, 6, 9, or 3, 6, 7, length 3. So that's the idea. Now, if you could computed longest of I, how would you find out the overall answer to the problem? Suppose you computed longest of I for each index.
Just find the greatest one.
Right, you look for the largest number in that array. And that would be the answer. All right, so that's a key idea. So here's the idea. I'm going to say to compute longest of I, well, it's at least 1. Well, I'm not going to try to explain that notation right now. I'm going to explain it through this example here. 7. That's a base case because there's nothing to the right to worry about. So the answer, what's the answer? What's the longest of that index going to be? Well, longest of 7 going to be 1. Okay. Now, what about for index 6? Well, to answer the question, you know it's at least 1. Then you've got to look at everything to your right. And what are we looking for? There's a J in this box. What are we looking for to the right? A letter larger than J. Some way to, if we start the subsequence here at J, we're looking to see where possibly could we go next. Well, there is nothing to the right of J that's bigger than J. We're talking about alphabetical order. So the answer there is going to be 1, right? Now we get to here. Index 5, there's an F. Which letters to the right of F are bigger than it? Just the j. So how do we decide what to put here?
One plus one.
Right, we look at, so j is at index 6. The longest subsequence that starts at index is 1. So we add 1 to it, and our subsequence length is 2. So we're just looking at some of the answers to the right. Okay? Now, here's 4. What indexes to the right of C, what letters to the right of C are here? All of them. So we look at all of the answers to the right, and we see one of them is a subsequence of length 2 rooted in index 5. The other is in length 1. So clearly, if we start at C, we want to go next to F. So what number do we put here? 3. Okay, so what I've done there is, in the animation, is I'm highlighting everything bigger than C. So we just take the max of the numbers under those yellow boxes, take the larger, add 1. That's C's answer. What happens with F? We look at the things bigger than F. There's only 1. So we take its longest. That's 1. We add 1. That's a 2. With H, same thing happens. We get a 2. What's going to happen with B? Everything to the right of B is bigger. So they're all possible next stops on our longest subsequence. But C is going to be the best next stop, because if we get to C, we can keep going and get something of length 4. And then finally E, there are those 4. You take the max of them, that's 2, and so we write a 3 right there. And now you're done. You found out the length of the longest subsequence starting at each spot. You just go through the whole thing and find out the max. That's a 4. So the best you can do is a subsequence with length 4. Okay? The math up here just describes doing that. It says to find what goes in the longest divide, you take the max of the longest of j's, where j is to the right of I. Well, we're things, this is doing the letter comparison here. So it's probably easier, if you understand this, you can figure out what the math means. From that, we can take that, that's basically a recursive program. This is a loop here. So we can write a recursive method that does this and memorize it and be done. Or can you see another way to do it besides writing a recursion and memorizing? Yeah?
Do like something similar to topological sort?
Well, not so much a topological sort. Did it take me exponential time to do it on the board here? So there's 2 options that we'll discuss for dynamic programming. One is to write the recursive algorithm and memorize it. The other is to build a table and fill it out systematically. So I was just systematically filling in the table from left to right, and it turned out to be an n-squared algorithm. So that just, I've raised a lot of issues today, and just barely touched on the topic. So you've got the weekend to think about it, and we'll dig in deeper on Tuesday.